Welcome. In this presentation, we will explore the concept of column store architecture. It is a modern approach to database organization. Instead of storing data in rows, data is stored by columns. Let's dive in and understand how it works. Before understanding column store architecture, let's compare it with the traditional row store architecture. In a row store database, data is stored in rows. As you can see in the left side illustration, each row contains all the information about a single entity, such as a person. The table shows the name, age, and city for each individual. On the other hand, a column store database stores data in columns. In the right side illustration, you can see that each column contains all the values for a specific attribute, like name, age, or city. This difference in storage has significant implications for performance and use cases. Let's explore the key characteristics of column store databases. Firstly, data is stored by columns and not rows. Secondly, column store databases are optimized for analytical queries. Thirdly, they offer better compression ratios as compared to row store databases. Fourthly, they are more efficient for read-heavy workloads, and lastly, they offer columnar data locality. The column-oriented storage diagram illustrates how data is organized. Each column stores a specific attribute such as ID, name, age, and city. This structure enables efficient retrieval of data for analytical queries because only the necessary columns need to be read. Column store architecture offers several performance benefits. It reduces input-output for analytical queries since only the necessary columns are read. It provides better compression as similar data types are stored together. It enables vectorized processing on column data and improves cache utilization. Due to its inherent architecture, it is efficient for aggregation and reporting. The query performance example shows an analytical query to find the average age by city. The illustration demonstrates that a row store reads all columns for each row, while a column store only reads the city and age columns, resulting in faster execution. Data compression is a crucial aspect of column store databases. Several techniques are employed to reduce storage space and improve performance. Some of the techniques are dictionary encoding, which replaces values with smaller numeric IDs; run length encoding, which stores repeating values as value count pairs; delta encoding, which stores differences between consecutive values; and bit packing, which uses the minimum bits needed to represent values. The compression examples show how dictionary encoding and run length encoding work, demonstrating significant compression ratios. Many database systems use column store architecture to optimize performance for analytical workloads. Some of the popular systems include Apache Parquet, which is a columnar storage format for the Hadoop ecosystem; ClickHouse, which is an open-source column-oriented database management system for online analytical processing, also known as OLAP; Google BigQuery, which is a serverless columnar data warehouse; Amazon Redshift, which is a cloud data warehouse with columnar storage; Vertica, which is an analytics platform designed for big data; and MonadDB, which is a pioneer in column-oriented database design. While column stores offer numerous advantages, there are also some challenges to consider. Column stores are inefficient for row-based operations like inserts and updates. They have row reconstruction overhead for queries needing full rows and transaction management complexity. They have higher implementation complexity and are not ideal for online transaction processing, also known as OLTP workloads. To address these challenges, there are several solutions and approaches. The solutions are hybrid storage models, materialized views for common queries, write-optimized delta structures, batch processing for updates, and vectorized query execution. Hybrid storage models combine the strengths of both row store and column store architectures to handle diverse workloads efficiently. These systems can dynamically switch between storage formats based on access patterns or maintain data in both formats simultaneously. Online transaction processing operations use row storage, while online analytical processing queries leverage columnar format. Background processes handle format conversion and adaptive query optimization. The hybrid storage architecture diagram illustrates how data flows between the row store layer, transformation layer, and column store layer. Column stores are ideally suited for specific use cases. Some of them are data warehousing, which involves large-scale analytical processing with complex aggregations. Business intelligence, which involves real-time reporting and dashboard analytics. Big data analytics, which involves processing petabytes of data with complex queries, and time series data, which involves analyzing sequential data points with temporal patterns. When choosing a column store, there are several decision factors to consider, such as workload type, data volume, query patterns, and performance requirements. Column stores are better for read-heavy analytical workloads over write-intensive online transaction processing. Here are some of the key takeaways. Column stores organize data by columns rather than rows, optimizing analytical query performance. They offer superior compression ratios due to similar data types being stored together. They are ideal for online analytical processing workloads with read-heavy operations on specific columns, and hybrid approaches combine the benefits of both row and column storage. Understanding storage architecture is crucial for database system design. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.